Welcome back. Part 2.
All right. Am I online? Yes. Thanks a lot. Welcome back. Okay, so let me just wrap up the two last slides very quickly and then give a different perspective on basically exactly the same thing. So I told you how we can use the construction of matrix product states to construct states which have some symmetry, like rotational invariance, by starting from rotationally invariant entangled states, and then again applying rotationally invariant maps. And I also told you that for this kind of model, we can also find some Hamiltonian by just looking at two sides of the model and observing that the state we start from cannot have all possible values of the output. And, well, we saw this by observing that we cannot get the spin 2 configuration because we start from something with spin 0 or 1. But in fact, we could have counted degrees of freedom because we only had 4 degrees of freedom and went to a 9-dimensional space. So it should have been clear from that point of view as well that this cannot work. And that's indeed the alternative way of looking at that. Namely, for a general matrix product state, not necessarily the example I gave, we can always ask, okay, let's look at a contiguous block of L sides, like before L was 2, and ask what can we say about the state of the system on this block of sides. And well, if we look at this reduced state here, which we get by kind of disregarding the rest, we know the state here, well, it has to live in the space spanned by these spins, which is a d to the L dimensional space, if d is a physical size of the physical system. Now, how many states can we possibly get? Well, all the entangled states in here are in a pure state, right? They have no degree of freedom we can choose. So the only degrees of freedom we have are the left dangling bond, so we can choose some value for the spin potentially, and some value for that spin. And that's all the degrees of freedom we have, so we actually only have d squared degrees of freedom, which, well, is a constant number. On the other hand, this d to the L, it will grow as we make our block longer and longer. It grows exponentially in the length. So you see that actually very quickly, pretty much regardless of how big these individual dimensions are, you will reach a regime where small d to the L, the dimension of the physical space, is bigger than the number of states you can get. So necessarily there will be states which you cannot get in the physical system, which earlier was a spin 2 subspace. Now it's just from a counting argument. And we can exactly the same way build a Hamiltonian by saying, well, let's choose an operator which is 0 on the states which we can get. Oops, this shouldn't be 1 minus, I guess, right? It should be the projector onto the kernel. So anyway, don't look at the formula, think about the intuition. We want an operator which is 0, a positive semi-definite operator like a projector, which is 0 on the states which we can get, and positive on the states which we cannot get, and we know there are such states from counting arguments. And then we put this everywhere in our lattice, we get a total Hamiltonian. It's again a positive semi-definite operator, which is 0 on the state we started from, so this is one ground state of that Hamiltonian. And again, it turns out that under very general conditions, which we understand well, this system will have a unique ground state. There will be no other ground state of that system. And there will be a spectral gap. So this framework can be really used to construct models which we can solve in the sense that starting from the wave function, we get a Hamiltonian and a wave function together, such that the wave function is the ground state of that Hamiltonian. So basically, this fact, together with the fact that that matrix product states approximate ground states of general gapped Hamiltonians efficiently, tells us that if we want to understand the overall structure of one-dimensional quantum systems, this is a framework which should be sufficient, right? Because every ground state is close to such a matrix product state, and then if we want to know if we can go from one state to the other one in a smooth, in a nice way, which doesn't change the physics abruptly, which doesn't cause a phase transition, we can stay in this framework because this framework comes with a Hamiltonian, right? So whenever we kind of smoothly try to go from one state to the other, this will also correspond to smoothly changing the Hamiltonian because, well, this whole Hamiltonian construction involves a finite number of objects, right? So whenever I change something analytically, I put a few of these guys together, it will still be a nice analytic and smooth function. The second thing I talked about was symmetries, and again, we can look at them in a general scenario, and I will do this now in the different picture of tensor networks. But that's, again, pretty much the same as before. What I say is that if I can start from one single tensor, which is invariant under some symmetry in the following way, that whenever I apply a symmetry operation, so that's supposed to be a matrix being multiplied with this index here. So whenever I transform the physical degree of freedom with some unitary, this is equal to transforming the entanglement degrees of freedom, the virtual degrees of freedom, with some different representation of the same group. putting a V on the left, so multiplying with a V on the left and a V dagger on the right. And now we can ask what happens if we start concatenating these things. We put together two of these guys. Well, what we get is that we get two of these objects on the right. So we have these two tensors, and when we connect, then we have to multiply them first with VG dagger and then with VG. But that's a unitary representation. That's what I'm assuming here. So they will just cancel out, right? It's V dagger V. It's the identity. So they go away. So all what remains is a symmetry action on the boundary of that region. And I can keep iterating that, right? And the symmetry action in the inside, in the bulk, will always drop out. I will only get symmetry actions at the boundary. So ultimately, by iterating this argument and closing my boundary conditions, I end up with this tensor here describing a wave function which overall is invariant under that symmetry. Now, the cool thing is that that's the only way of obtaining such a symmetry. So whenever I know I have a wave function which is invariant under that symmetry, I can actually show it must come from such a local encoding of that symmetry. So it's really a full characterization. Symmetries in matrix product states can always be encoded locally. And that's great because the local description is very closely related to the structure of the Hamiltonian, just as in mean field. And in particular, if I derive my parent Hamiltonian, it's derived by looking at 2 or 3 or whatever sites built from this tensor or this map. And if I start from an object with a symmetry, I combine a finite number of them, the new object will have exactly the same symmetries. So I will also get a Hamiltonian, just as for the AKLT model, in the general scenario, which will inherit all symmetries. So in some sense, it really forms a framework for kind of starting from a tensor, on the one hand building a Hamiltonian from it. This picture kind of illustrates that what the Hamiltonian does, it makes sure that locally the system looks like it's built from the tensors I'm looking for. So it's built from the local reduced density operator of the tensor. So this allows me to get a Hamiltonian. The tensor, of course, by itself already defines a matrix product state. That's supposed to be a big system. And this will be exactly the corresponding Hamiltonian, which has this guy as a ground state. So I can really build like families of solvable models by playing with a tensor, not playing with Hamiltonians. And let me, by going back to the AKLT model, illustrate how this allows us to understand some of the non-trivial physical properties of this model, which it actually has. And to this end, let us take the AKLT model and put it on a chain with open boundaries. Now, if you remember, the AKLT model had spin 1s here on the physical system and spin 1/2s here on the virtual system. And now I can ask, given the parent Hamiltonian, what are the possible ground states of my system on open boundaries? And well, the parent Hamiltonian is constructed in a way where it makes sure that it's kind of built this way. But of course, I can choose whatever boundary condition I want. So these green spins here, I can put to any value I want, and just by construction, this will be a zero energy ground state of the Hamiltonian. Now, why is this noteworthy? It's noteworthy because my spin chain consists of spin 1 particles. However, at this edge, at the boundary, this spin 1 chain has excitations with zero energy, gapless excitations, which have spin 1/2. Now, out of a spin 1 system, usually you cannot get spin 1/2 degrees of freedom, because whatever you do, you have a spin 1 chain, you flip a spin, you decrease a spin by 1, not by 1/2, right? Whatever you do, you would expect to stay with integer spin. So it's pretty amazing that if you put this thing on a chain with open boundaries, at the boundary you get something which is not even contained in this model somehow. You get half integer spins. And that's what's called fractionalization of the spin. So the physical spin at the boundary fractionalizes. And in this picture, there's a very natural way to understand it. It's exactly because the spin 1 chain is internally constructed, built from spin 1/2 particles. And well, that's indeed, if you think in terms of mean field theory, it's impossible. You have spin 1 particles, the only way of building excitations is flipping them. It will change the spin by an integer amount. So with a spin 2 chain, you might be able to get spin 1 particles or something like that, but you will not be able to get spin 1/2. So getting half integer spins is a non-trivial property. And that's really related to the fact that the physical spin 1 transformation breaks down into 2 spin 1/2s here on the left and on the right. And this can actually be shown that this is really a non-trivial topological phase. So actually, this is an example for a state in the Haldane phase, which is one of the discoveries for which Haldane got the Nobel Prize last December. And the point is that using this framework, we can indeed show that it's completely impossible, basically using this framework saying, okay, whatever I do to smoothly change my Hamiltonian, I can mimic this by smoothly changing my tensors. it's impossible to change these tensors smoothly in a way where during this smooth change, the spin 1/2 will smoothly change into a spin 1. And the reason is really that there's no way of combining spin 1/2 and spin 1 and jointly having them transform nicely. That's not something which transforms nicely under rotation. So this is really a way in this picture to really understand why some system can behave in a very unconventional way, because the physics it exhibits at the edge is something which kind of is in a non-trivial way related to the physics of the system in the bulk, in the overall system. Okay, so this is kind of the end of the MPS part. So the important part here was to realize that matrix product states can encode physical symmetries in a local fashion, which allows us to get kind of a very close relation to Hamiltonians, which can be used to model the physical properties, the symmetries, into this local description, because it will be reflected in the Hamiltonian, and then to study how these systems behave. And indeed, this turns out to be a very powerful tool for studying phase diagrams, the different possible phases of matter for strongly correlated for entangled quantum systems. But okay, for the second half, I really would like to go to two-dimensional systems and sketch some idea for 2 dimensions. And there, the resulting class of states is called projected entangled pair states, or, well, tensor network states again, of course. And the idea is very similar to 1 dimension, so we really follow a very similar route. So one way of looking at it is saying we place entangled states along a square grid, then we block 4 of them here, and we apply some linear map which singles out kind of the degrees of freedom of interest. So again, you see that from the construction, these states will satisfy the area law, right? Because again, when we cut a block, we cut a certain number of bonds only sitting at the boundary. We can again write this in terms of tensors. So if you write it in terms of tensors, we would start from some 5-index tensor, which again has 1 physical degree of freedom pointing up, and 4 auxiliary, 4 entanglement degrees of freedom, which are kind of going to the next neighbors. And then we can build a 2-dimensional grid, really using the same language as before. Whenever we connect a leg, it means we identify that leg and sum over it, which again, it's just the same derivation as before. That's exactly what this maximally entangled state does. It's basically a delta function ensuring that that degree of freedom and that degree of freedom are equal. So we can then build 2-dimensional grids with some bond dimension capital D again and a physical dimension small d. And this is, well, denoted, often called projected entangled pair states, which kind of comes from this picture where you put entangled pairs and then apply some linear map, but not necessarily a projection. Or we can, of course, term them tensor network states, because again, the idea is that we have the general expansion coefficient of a state on a 2-dimensional system, and we express this overall expansion coefficient, this multi-index tensor, by contracting a set of simple tensors according to this 2D grid. Of course, we have to talk about boundary conditions in principle. We might wrap the system on a torus, close them periodically. We might also just terminate these boundary conditions by omitting these outside indices at the boundary of some finite patch. There are different ways of doing that. Now, it turns out, but I won't really talk much about that, that these states, also with less tight bounds, also approximate ground states of local Hamiltonians well. They again form a complete family, and if you think in terms of the teleportation picture, it's again clear. I can place a whole state in the middle and use the entanglement to teleport it everywhere. I should also say that, of course, we can keep continuing and going to higher dimensions. We can do this construction on a 3-dimensional grid. We can do it on different lattices, right? There's no reason to use a square lattice. Indeed, one would intuitively expect that the overall lattice, of course, should come from the way the interactions go, right? So one could use triangular lattices, hexagonal lattices, whatever is actually needed for the physical system under consideration. But I will mostly stick with square lattices. Of course, in some sense, if we're only interested in the overall structure of these systems, square is pretty good, because whatever lattice you have in 2D, you can build unit cells and get a square lattice. One has to take care how to break it down, but the overall structure is well reflected in a square lattice. Now, we can do pretty much the same we did in 1 dimension. So we can ask, how can we encode symmetries? And well, we can encode symmetries pretty much the same way as we did in 1 dimension, right? We can say whenever we act with a symmetry in our physical system, we demand that this corresponds to such a product of different symmetry representations again, acting on the entanglement degrees of freedom in a way where we have V and V dagger on adjacent sides, and here V and V dagger. So we can do the same again. We can concatenate these guys. Whenever we concatenate two of these guys, the V and the V dagger will cancel out. We keep growing. And then if we go to an extended system, like on a torus, we will get a wave function which is invariant, right? Because all these symmetry actions on contracted indices have canceled out. Now one can ask, is that the only way of realizing symmetries? And the answer is we don't really know. We know conditions under which this is the case. But we also know that a number of interesting cases don't satisfy this condition. So that's kind of still an interesting open question. What is the most general way of realizing a global symmetry locally? So if I have two states which are related by a symmetry, how are the corresponding tensors related? In one dimension, we knew that this is the only way. In two dimensions, of course, we know that this is sufficient, but it's not clear if this is necessary. We can also, just as in one dimension, define parent Hamiltonians. And again, the idea is very similar. We look at some patch of our system. We look at the possible physical states we can get at this patch. And again, the number of states we can get is parameterized by the degrees of freedom at the boundary, which is, well, which goes as a linear system, the linear block size, right? It goes as a boundary. Whereas the space in which these states live corresponds to the bulk. So it grows like the volume of the bulk. And of course, the volume of the bulk grows much faster than the volume of the boundary, the size of the boundary. So again, if we look at sufficiently big blocks, we are guaranteed that not all states can appear. So we can always write a non-trivial Hamiltonian, which only gives energy 0 to those states which can actually appear. Or a different way of saying this is saying that the parent Hamiltonian makes sure that locally, if we look at a small patch, say 2 by 2, the state looks like that. It looks like it's being built from the correct tensors. Now, we know from tiling problems and things like that, if we make sure that locally something looks correct, it doesn't mean that globally everything is correct, right? There could be a twist somewhere. It should just be in a way where you cannot kind of see it locally anywhere. And we'll see examples of that, actually, in a moment. And again, this would form a framework for kind of studying systems by trying to encode things in the tensor. From that, we get a Hamiltonian, which again inherits all symmetries. We also get a wave function, which is a ground state of that Hamiltonian. And we might be interested in asking, well, what is the structure of the ground space? What is the spectrous property of the Hamiltonian, and so on. And again, well, as for the symmetries, we don't have a full characterization of the ground space, and in particular not of the spectral gap. But we have partial results. We have conditions under which we know that the ground state is unique. And also, what I will show you later, we have conditions under which we can show that the ground space has a topological degeneracy, which allows us to study topological phases. I should have added, I didn't say this on the last slide, right? I said it's approximate ground states well, but in particular, what we also know is that we can take models which have topological order and write them exactly in that form. And we will see this in a moment, actually. Okay, so let me just spend one slide on computation with PEPS. Just an analogy to the one-dimensional case. And let's ask again what happens if we want to compute expectation values for these two-dimensional states. Well, basically, well, you know, the pictures are getting messy. You have to take the state in the ket, in the bra, you contract them, and you put some operators here and here, say, and you want to look at the correlation function. But the same picture would hold if you have a single operator, you compute energies. And now, well, like before, we said we can do kind of a top view, right? We can cut this into vertical slices. So we define these E operators again, which are the ket and the bra together. We have some E with the operator in between. And now that's a top view of this thing, right? So it's a two-dimensional grid of tensors, which now have a dimension d square rather than d. So it's all nice, controlled dimension and so on. And we can again ask, okay, how can we compute things here? And we could say, okay, we multiply this from bottom to top. We could again define a transfer operator, which tells us how correlations from anywhere here are mediated to here. So if we know the spectrum of this transfer operator, we would again know how correlations decay and so on. Now the point is, of course, this transfer operator is much more tricky. Before, the transfer operator was like a quantum channel, right? It was something operating in a fixed dimensional space. Now this is something operating on a one-dimensional system, on a chain by itself. It is again a completely positive map, but it has a very intricate structure, and it's actually an open question to really understand the overall structure of these kind of operators, of quantum channels, which themselves have a one-dimensional structure in them. So now the question is there a way to kind of efficiently do these computations? And it turns out there's not, because, well, what we have to do is we have to sum up these indices in some way. And in the 1D chain, we could just multiply matrices. And the way it worked, the reason it worked was that at every time, whenever we multiply a bunch of matrices, the degrees of freedom are those sticking out of the block where we multiply the matrices. So we can try the same here, right? We take this grid, we start with one guy, we contract one index, we get this block here, we contract with some more indices, we get this block. But you kind of see, regardless of which way you do that, you will always, at some point, end up with a block where the number of degrees of freedom is kind of, well, they're sticking out at the boundary. At some point, your block is on the order of the system size, like half the system or so. So it means that the number of degrees of freedom grows exponentially in the linear system size. That's still better than the actual number of spins. It's only the square root, but it is exponential, right? So it is prohibitive doing these calculations for big systems. Indeed, it turns out it's a computationally hard problem. This contraction problem contains instances which are computationally hard, so you cannot expect to do it efficiently in the general case. So in these cases, we have to resort to approximation techniques to compute expectation values. For instance, you could cut this into 1D slices and try to approximately diagonalize this transfer operator by, again, treating it as a one-dimensional object and using matrix product states for this computation. So these methods work, but they're much more subtle than in one dimension. So I won't talk more about that. So as I said, well, these projected entangled pair states, they allow us to approximate two-dimensional systems faithfully. They can be used for numerical simulations, although it's much more challenging. And we can also use them to model the physics of two-dimensional systems by locally encoding symmetries. But now I would like to move on and not talk about systems with physical symmetries, but talk about systems with global topological order, because these are the kind of interesting, exciting, exotic phases which we have in entangled quantum systems. And I would like to convey how these systems can be described within this framework, how we can understand within the framework of tensor networks where this topological order comes from. And the kind of remarkable thing is that we will see that the topological order is related, again, to a local property, which is kind of amazing given that it's actually something which shows up in the global entanglement and not locally in the system. Nevertheless, there is a local way of explaining that. And for that, well, let me first start by introducing one topological model. Probably many of you have seen this before, which is kind of the simplest topological model, the so-called Toric Code model, which has been proposed by Kitaev as a way to store quantum information. And the idea is that what we have is we have a square lattice, and we have qubits living on the edges of the lattice. So each edge corresponds to one qubit. And what we do is that if the state of the qubit is 0, we just leave the line black. And if the state of the qubit is 1, we mark the line in red. And now we want to build a Hamiltonian, a system, which in its ground state has a superposition of all possible closed loop patterns on this lattice, right? So on this lattice, we can draw closed loop patterns. This corresponds to a configuration of zeros and ones. And we want a system which in its ground state has an equal weight superposition with always the same +1 phase of all these loop patterns. So I won't write the Hamiltonian, but to convince you this is possible, we want two kind of terms in the Hamiltonian. One should make sure that loops are closed, so it should make sure that there's always an even number of ones around each vertex. So it's a term acting around the vertex. And then we want terms which ensure that we have the same phase. So these should be terms which take a plaquette, like this one, and flip it. Flipping the plaquette means that I take this loop here and move it like that. I can then flip another plaquette, I straighten this loop, and we can have Hamiltonian terms which couple two of these guys by actually flipping that and ensuring that the ground state has an equal phase. So trust me, it can be done with local Hamiltonians. So we can write local Hamiltonians, which kind of make sure, well, each vertex is fine, and at a phase flip, everything goes well. Flipping a plaquette, the phase stays okay. Now, this should indeed, one would think, have as a ground state all possible loop configurations. If these local plaquette flips allow us to connect all possible loop configurations with each other, and if you think about it for a while, you will figure out that this is almost correct. However, if you start from a configuration which has a single loop going around the torus, you will never be able to remove this single loop by flipping individual plaquettes. And one way of seeing that is by actually takes this configuration. It has one loop going from the top to the bottom of the torus. And whatever plaquette you flip, you will never be able to kind of to make this loop go away. And the reason is that if you make a cut like this, so this horizontal green dotted line, and you count how many loops cross, it's 3. You flip a plaquette, you might change the 3 to 5. The 3 might stay a 3. Right? You flip this plaquette here, the 3 stays a 3 because you move this line here. You flip this plaquette, the 3 becomes a 1 because you take these two lines and you remove them. But you see, you can always only change this number by 0 or plus minus 2. You will never be able to change it by 1, which means that the fact whether you have an odd or even number of loops running around the torus is something you cannot change. So they're actually decoupled ground state sectors because they're only characterized by a global property. And this model, therefore, has finally 4 possible ground states, which are characterized by whether an even or odd number of loops goes in horizontal and vertical direction around the torus. And this is exactly what has been proposed by Kitaev as a way of storing quantum information in that ground state. Now, this model also has non-trivial excitations, and one way of seeing that is that one way of building an excitation is putting not a closed loop, but an open loop, break a loop open. Obviously, each open loop has 2 endpoints, right? Each string must have 2 endpoints. So these excitations do come in pairs. The other thing is we could screw up the phase. We could say if we flip a plaquette, we don't put a +1 relative phase, but a -1 phase. These also have to come in pairs. And one way to see it is if you do a sequence of flips and you come back, you should better have an even number of -1s. Otherwise, you kind of screw up your total phase. You get an inconsistent relation of these phases. So it turns out that these things have to come in pairs. So this model is really one of these topologically ordered models, which has a ground state degeneracy, which depends on the genus, right? Because if I would put something like that by twisting my lattice on a sphere, there is no non-trivial loop going around the torus, because I can just, well, smoothly make this loop go away. Now, how would a tensor network representation of such a model look like? For this, let's start from the superposition of all possible loop patterns. And we cut the superposition into small pieces. So we cut it into blocks which contain 1 plaquette each, as indicated by these blue lines. And let us now look at one blue box. And each of these boxes will be described by a single tensor. So what does this box contain? Well, it contains a part of a loop pattern. So we can look at this box and say, OK, if we have some loop pattern in such a box, what do we have to say? Well, we have to say where does a loop enter the box and where does a loop leave the box, right? And whenever a loop enters this box, we put a 1 on the boundary. And if no loop enters or leaves the box, we put a 0. Right? We cut this into pieces. Every piece will have a piece of this loop pattern. It enters somewhere, and it has to leave somewhere because we don't have open loops. Now, we can write a tensor which indeed encodes all these superpositions. So the entanglement degrees of freedom tell us if a loop leaves the box at a certain position. And the physical degrees of freedom actually describe the loop pattern on the inside. So now what you see is due to the fact that we must have closed loop patterns, whenever a loop enters the box, it must leave it. So we always have an even number of 1s at the boundary, right? Because, well, a 1 means loop enters or leaves, and the loops cannot stop in the middle. There must be an even number. Now, what does this tell us? Well, it tells us if we look at this tensor, we count this number of leaving loops. We can write an operator which does this counting, which is a Z matrix, right? A Pauli Z matrix, which gives me a +1 if I have a 0 and a -1 if I have a 1 at the boundary. And all configurations at this boundary must have an even number of +1s. So it means if I multiply this tensor with a Pauli Z on all the entanglement degrees of freedom, I must get +1, which is just a reflection of the fact that there are only closed loop patterns, right? There's a parity constraint on loop patterns. It's reflected in a parity constraint on the entanglement degrees of freedom. So this tensor turns out to obey some parity constraint. Now, this in some sense looks very similar to the constraints we had for physical symmetries, right? In that case, we acted with a physical symmetry action and translated to this. But in some sense, it's very different, right? Because there's no physical action involved at all. So it's not a symmetry, it's a constraint. It really tells us that, that this tensor is constrained to configurations which have even parity. So let's look at this constraint and ask, is that maybe the feature of the topological order? Because it indeed relates to the fact we have closed loops. And see if we can explain and understand the topological order from such a symmetry, which is really a property, a constraint on the entanglement in our system. So for this, I would like to rephrase the symmetry in some way. So this is just the equation we had before, right? We said the tensor is invariant by multiplying it with a z on the entanglement degrees of freedom around the tensor. And now I put these dotted lines. This is just to think that basically these z's form a circle. They sit in a circle around that guy. It tells me such a circle can be made to go away. I can remove such a circle. Of course, now I can rephrase it. I can take two of these z's and put them on the other side of the equation. Say I took these two z's and put them on the left. I get this expression. Now, again, I put a dotted line, and my idea is to think that these z's are lined up along this dotted line, and I can push these z's through the tensor, right? They're lined up on the top of the tensor. I can push them so they're aligned on the bottom of the tensor. Or I can put one on the other side. This means I have a string of z's, and I can deform them to kind of make a turn under the tensor like that. So we can start building these things up in a bigger system. This tells me that if in a bigger system I make a string of these z's, so the green line is just the same as a dotted line here. It's just kind of a guide to the eye. So whenever I align these z's along a loop, a string, I can take this string and deform it, and I can keep deforming it using these equations, right? So I can take one of these closed strings and start moving it through my state, through my tensor network, and I describe the same state because it's a symmetry of my description, right? So the string is really, it's like a floating object floating around in the system, which in particular means if there's one of these strings floating around anywhere in my system, it will be something which is invisible to the parent Hamiltonian, right? Because what does a parent Hamiltonian do? Well, it looks locally, and whenever the state looks like it's built from the original tensors, then it gives it an energy 0, so it's happy, right? Now, when this guy acts somewhere where there's no string, it's certainly happy. Now, it could act somewhere where the string is running, but because the string can be smoothly moved through the lattice, we can just take the string and move it away and say move it at the bottom. We can move it around this Hamiltonian here, and it will describe exactly the same state. So this tells us the state actually looks completely fine everywhere, right? Despite having the string, the state actually looks completely fine everywhere, so it actually is a ground state of our parent Hamiltonian. So let me remark that in some sense, indeed, the essential philosophy here is that we can form strings of objects which we can smoothly move. This can be used to generalize this considerably from this Z2 case to general groups and beyond general groups. I won't talk about that, but the idea is really that we can build floating strings, and starting from that, you can build a very general language to describe topological phases in this picture. So we've seen we can take these strings, we can put them on our lattice, and the parent Hamiltonian won't see them because they can be freely moved. So let's see what we can use this for. And one thing we can use this for is to build different ground states of our system by taking a torus and putting one of these strings in horizontal direction and another one in vertical direction. Each of these strings could either be a z or the identity, so putting no string. And, well, we have two of these strings. Again, they're freely floating, freely moving. So it's a ground state of our original Hamiltonian. But it turns out this is actually a different state, right? And of course, I would have to prove that to you. It could still be the same state, but at least it's not evident it's the same state, because indeed this loop can be freely moved, but it cannot be removed. And the reason is that it wraps around the torus, right? So there's some kind of winding number. If it would be a closed loop somewhere, we could make it smaller, 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 and it would go away, because the very last condition tells us small loops go away. But if it goes around the torus, there's no way of making it smaller, right? Because it goes around the torus. So indeed, these should be 4 different states, and one can indeed prove that this Hamiltonian has these 4 states as a ground state, and it has only these 4 states as a ground state under some condition, which is basically saying that the symmetry is the only constraint on our tensor. So it shows that indeed, once we have such a symmetry, the system should describe something which has topological order encoded in it. So one thing, and I think that's actually, that's really great, it's a local way of understanding a system is topologically ordered, which is very surprising given it's actually an ordering in the global entanglement. Of course, the trick is that the local characterization involves these entanglement degrees of freedom. We have a local constraint on the way in which the entanglement is being built up, which in the end, even on a global scale, gives a constraint. It's actually also useful to kind of study these things, to model these things. It gives us a way to capture the whole ground space manifold starting from a single tensor. So we get many states from a single tensor and knowing how its symmetry looks like. And we can also explicitly do numerical constructions, for instance, that way. So one thing you might say, oh, I started from the Toric Code. All I showed you is an alternative proof that the Toric Code is topological. It's not true, because all I used in this argument is saying, well, we have a tensor which has this kind of symmetry, which of course is satisfied by the Toric Code. But just by parameter counting, you can see there are lots of tensors which satisfy this, right? Because this is kind of just canceling half of the degrees of freedom of the tensors. The other half is still there. So there are lots of states. In particular, there are states which have finite correlation length, which usually are very tricky to deal with. If you want to argue how you build these different ground states for a system with finite correlation lengths by acting on the physical system, it gets kind of pretty nasty. These operators get widened and so on. Whereas here, this is a strictly localized string because it tells us how the entanglement is modified. We can also use this to study excitations of systems. So we can build exactly the same strings, but we could leave these strings with open ends in our system. Now, the same argument as before will tell us that the Hamiltonian, say, acting here, will accept this as a zero energy state, right? Because the string can be moved out of that region. It can be moved anywhere. But the endpoints are special. So actually what is special about the endpoint is a plaquette at which it ends, because adjacent to this plaquette, there's an odd number of z's. There's like one z. And what our symmetry action can do is it can change the number of z's adjacent to each plaquette by 2 or by 0, but it cannot change it by 1. So the string could leave in this direction. I can move the string to leave in this direction and go like that. But the fact that this plaquette has an odd number of z's adjacent to it cannot be changed. So these endpoints in particular are not of the form that parent Hamiltonian likes, right? Because they don't look like, I mean, at least it's not clear that they can be made to look like they're built from the correct tensors, and indeed they cannot. So these two endpoints here will indeed be excitations. So what we've built is we have built something which forms a pair of excitations. It's impossible to build a single one because the string has to end somewhere again. So these are excitations which come in pairs. And the thing is we can also build a second type of excitation, namely we can take one tensor out of our tensor network and replace it by a tensor which transforms odd under the symmetry, which has a minus sign here. Now again, this is not a local excitation in the sense, well, it's local in the sense that it can only be seen by a Hamiltonian acting around here because everything looks fine. But we cannot create it locally because creating things locally means touching the physical degree of freedom with some linear operator. And this will never be able to change an entanglement constraint, right? Because this has nothing to do with the physical degree of freedom. We cannot create this guy locally. Indeed, it has to come in pairs. And one way to see it is that if you close your boundaries, the overall object has to transform trivially under this z-symmetry. Now, this transforms odd. So you must put an even number to get an object which transforms nicely. And the cool thing is if you now take these guys together and you ask what happens if you take one of these strings and move it around this guy in a loop and you have somehow a way of moving it and making it go away, then, well, creating a pair, moving them and putting them back together will leave as a trace a loop of z's going around this guy here. So now we know we can make the loop smaller, but when we make it go away, we see we get a minus sign. So what this tells us is that these two types of excitation should have some non-trivial mutual statistics among them. Okay, so this really tells us that we can model the excitations and again study the behavior of excitations in these systems. And well, the message maybe to be taken from that is that this tells us that topological order in PEPS can be really modeled, explained based on some local symmetry, but it's a symmetry acting on the entanglement degrees of freedom and not on the physical spins themselves. How much time do I have left? Just 15 minutes. Okay, let me maybe just spend one slide. So you might say, okay, this is very contrived to have these symmetries on the entanglement degrees of freedom. because I kind of started from the Toric Code, which is topological. I analyzed it. I found this constraint on the entanglement and said, OK, let's ad hoc impose it. This is very much different from what I did earlier, what I tried to explain earlier, to say, oh, we want to look at a system which has certain physical symmetries. Let's try to incorporate these symmetries into the local description, right, which are physically motivated symmetries. These, in some sense, I mean, they're not related to the physical degrees of freedom. So how could we motivate them? Well, for instance, let's try to build a model which has a physical spin 1/2. So we have a model which transforms under a spin 1/2 of SU2, so it just transforms under SU2. And we would like, there's something missing, it's popping up in a second, we would like to put some representations here in a way that if we act with a spin 1/2 here, this transforms in some way. So let's try putting a spin 1/2, okay? So remember, this was UG, and they had VG, VG dagger. I'm just writing the representation now. So my first attempt would be to find a tensor which encodes my physical spin 1/2 like this. Now let's count on the right side. Well, 1/2 times 1/2 is 0 plus 1. The other one is also 0 plus 1. Together they give 0, 1, or 2. But the main point is they give an integer spin, right? I take 4 half-integer spins, they're integer. That's integer, that's half-integer. Very bad, I won't find a solution, right? You could put integer spins on the right, but this will be equally bad, right? It will also be integer. So there's no way to satisfy this equation. So it turns out the only way to satisfy this equation is to mix integer and half-integer representations here, right? Well, I mean, I'm not sure how contrived that is. You could think of it's a bit like a TJ model, which has, well, either a spinful particle or no particle. But in any case, well, you could say, so what? That you have to combine it. But if you look closer, what happens, you will figure out that, of course, to get a spin 1/2, or generally a half-integer spin here, you have to combine, say, 3 spin 0s and 1 spin 1/2, or 1 spin 0 and 3 spin 1/2s, because there's this integer half-integer effect, right? So you have to combine an odd number of half-integer spins to get a half-integer spin. So it means there's a parity constraint here, right? I must pick an odd number of spin 1/2s. Well, first of all, you must combine these guys, but then you must pick an odd number of spin 1/2s. So which means if I write out an operator which counts how many spin 1/2s I have, so it puts a -1 on the spin 1/2 subspace and a 1 on the spin 0 subspace, then my tensor must transform odd under this counting operation. Right? So just from the representation theory of SU2 and the fact that I encode it as a tensor product, I obtain a constraint on the entanglement degrees of freedom. This is very close to what we had before, except for the minus. But you know, if you put 2 of these guys together, the minus will go away. But conceptually, it tells you that you can indeed get such a constraint just by looking at the representation theory of your physical symmetry. Just by looking at the way in which you encode your physical symmetry, this could trigger some underlying symmetry on the entanglement degrees of freedom, which in turn, again, could relate to topological order. So this entanglement symmetry can actually come from a physical symmetry, and understanding the general way in which this happens is still something which is open, and that's actually a very exciting question to understand this general connection, which, for instance, relates to the most general way of even encoding this physical symmetry, maybe not as a tensor product. Okay. I think I will skip the next 2 slides, which give an example of something which is an SU2 symmetry, which are resonating valence bond states. You can ask me about that later. It's actually a very powerful way of analyzing them. But let me spend the last couple of minutes to talk about entanglement spectra and the role of the boundary. So what is this about? Well, it's about what happens at the boundary, the edge of topologically ordered systems. And it's well known that the edge of topologically ordered systems can exhibit very exotic physics. So what is very famous is in the fractional quantum Hall effect, or even the integer quantum Hall effect. At the boundary, you have very precisely quantized edge currents, which are robust to any kind of physical perturbations. So you have a one-dimensional boundary, and the current flowing in that boundary is exactly quantized. And that's a very exotic behavior in the following sense, that if you would try to write on a one-dimensional Hamiltonian, describing an actual one-dimensional system, you cannot get this kind of physics in one-dimensional systems. So these systems look like one-dimensional systems, these edges, because kind of if the current is only conducted at the edge, for instance, but it cannot be described as a one-dimensional system. So people would say that this system has an anomaly. And the point is that the reason why it has this behavior which cannot be described as a one-dimensional system is because it is not a one-dimensional system. It's a boundary of a two-dimensional system. And the fact that this two-dimensional system has some non-trivial order in its entanglement allows it to behave in a way in which truly one-dimensional systems could never behave. So that's point number one. The physical edge, what happens at the edge of a system, which is topologically ordered, can be something which behaves in a way which cannot happen in an actual one-dimensional system, which reflects the fact that there's topological order in the bulk of the system. The other thing is looking at entanglement properties, at Schmidt decompositions, and that's something which has been first proposed by Lee and Haldane. What they did is they took a fractional quantum Hall state, they chopped it in two halves, they put it in a sphere, and then they did a Schmidt decomposition, and they thought of the Schmidt coefficients as Gibbs weights or as energies. So they wrote them as quasi-energies EI. And well, because the system has symmetry, it's rotationally invariant, their Schmidt decomposition states have the same symmetry. So they also have rotational symmetry, which means you can assign a momentum to them. So what they did is they said, oh, this gives us an entanglement spectrum labeled by a momentum, a one-dimensional momentum. So they said, oh, it's a one-dimensional momentum. We should be able to interpret this as something which is a spectrum of a one-dimensional Hamiltonian, and well, eigenstates of a one-dimensional Hamiltonian also have a momentum quantum number if it's translation invariant. So they plotted this, and well, I don't see much here, but they certainly saw that the spectrum is very close in its essential features to the spectrum of the theory which describes the actual physical edge of that system. If I would actually chop this fractional quantum Hall state, and look at the edge physics, which before I told you is quantized and has all these kind of robust properties, the theory, which is a so-called conformal field theory, which describes this, has exactly the same spectrum. Well, not exactly the same, but the important features are the same. So they said, well, by looking at the entanglement of such a system, we can actually infer something about the actual edge physics of that system. And we should think of basically the entanglement spectrum as coming from what they called an entanglement Hamiltonian sitting at that boundary, which should be a one-dimensional Hamiltonian. So, of course, this is kind of tricky because the entanglement spectrum is a property of this part of the system being entangled with that part. So it's pretty unclear why this should be described by a one-dimensional Hamiltonian. And if yes, what should be the underlying space, how you could even derive it or obtain it. So can we understand this relation better? And that's something where tensor networks turn out to be very powerful. And the reason is that, well, if I look at a two-dimensional system in a tensor network formulation, I take a 2D system, could be a sphere, torus, whatever, I cut it into two halves, and I look exactly at this kind of entanglement spectrum. So I have a left half, I have a right half, and I look how they're entangled. Well, they're entangled over a summation index. And I already said this earlier, right, in the 1D part. If I cut the system in two halves, this summation index is basically exactly given by all these degrees of freedom sitting here at the boundary, right? I1 to IL assigned to these guys here at this boundary. So the entanglement is basically parameterized by the degrees of freedom, the entanglement degrees of freedom at the boundary, which first of all gives me an explicit one-dimensional structure in the sense of being a tensor product with like a geometric notion of sitting along a chain. It actually also gives me an explicit Hilbert space here with a fixed dimension D. So this way we can, for instance, numerically compute some entanglement Hamiltonian by really computing the way how these guys are entangled over this cut, doing a Schmidt decomposition in these parameters and going to the eigenbases if you wish. We can also use it to analytically understand what the degrees of freedom are, right? The degrees of freedom are exactly the degrees of freedom sitting at this boundary here. One noteworthy thing is, again, this system here is if it has some physical symmetry. We have seen that physical symmetry is reflected on the entanglement degrees of freedom. Consequently, this will show up exactly at the boundary, right? This boundary space here will be equipped with exactly the same symmetry actions which my bulk system had. So you can infer a lot about the structure of this boundary by looking how you encoded the physics locally into that system. So this is the entanglement spectrum. The other point was, what is the edge physics, right? So what are the low-lying excitations of the system when I put it on a region which has a boundary? And again, if we do this, it turns out that in tensor networks, or in PEPS, the the low-lying degrees of freedom are exactly parameterized by the different boundary conditions here indicated by red dots I can put at the boundary, or in this projected entangled pair picture, again, by the value of the spin sitting at the boundary I put before applying the PEPS projection. And the reason is that, well, the parent Hamiltonian makes sure that locally the state looks correct, right, like being built from the right tensors, which means I shouldn't mess with the bulk, because if I replace tensors in the bulk, this will probably screw the system up. But if I put a different boundary condition, well, the Hamiltonian, of course, is built exactly such that it accepts all possible boundary conditions as valid ground states. So actually, regardless of what boundary condition I choose on these red dots, I will always get a state with zero energy. So kind of the low-lying excitations are they're actually completely flat, right? They all have zero energy. And they're characterized by choosing different boundary conditions. So again, I get an explicit space which describes kind of what kind of the structure of the physics at the boundary should be. Okay. So, well, this can be used as a computational tool and so on. But the point I would like to make is to see what happens once we go to topologically ordered systems, which should have robust properties at the edge, which are anomalous in the sense that we cannot get them in truly 1D systems. So let's try to see how these two things are reflected at the edge. And remember, in both cases, both here and on the slide before, the degrees of freedom sitting at the boundary were the ones which kind of were giving me both the entanglement properties and the edge physics of the system. So if I have some system which is topologically ordered, remember what we had is that the entanglement degree of freedom had some constraint given by some symmetry operation like Z. So if I look at a bigger patch, what will happen, of course, is if I take these guys and I will multiply them, I see that this bigger patch has exactly the same symmetry action at the boundary, right? So this is a stable constraint. This constraint of having even parity will be stable as I make my blocks bigger and bigger. So it means that whatever physics, whatever state I describe at this boundary, it's pretty much unconstrained except for this parity constraint, which is a global constraint, right? So it tells me that, well, the boundary degrees of freedom can be pretty much anything they want as long as they have even parity under the Z, which is a very non-local constraint, right? So for instance, it tells me that if well, one thing I didn't mention this, but if you know about topological entanglement entropies, it tells me that the entropy of this region, it's pretty much anything, but it's constrained to the even parity sector, which will give a factor of 2 in the dimension of my Hilbert space. So in terms of entropy, it will give a log 2 correction. If I look at the entanglement spectrum, so the way in which these degrees of freedom are entangled with a boundary, with the outside, it can be anything you want, but it will be projected to the even parity subspace, because this can only happen in the even parity subspace. So I could have something which is described by some one-dimensional Hamiltonian, and then projected to the even parity subspace. This projection is completely non-local. It's nothing which I can obtain as any thermal state of any local interaction. So one way to understand it is to say I have a local Hamiltonian, and then I have to add a second term, which is topologically. It's a non-local term and a non-local projection, which hits a system like an infinite temperature. It's completely unphysical, both the temperature and especially the locality structure. So that's kind of an anomalous term showing up in this Hamiltonian. So we can understand where it comes from. It comes from this local symmetry. Except for that, the Hamiltonian is all normal. It's just this one extra contribution, which relates to the topological order, to the symmetry structure encoded here. And if I would have a different symmetry, a more general symmetry, I would get a different anomalous term here, so related to the topological order in the bulk. Then for the edge dynamics, I would get the same. So if I look at the edge physics, again, I could put whatever boundary condition I wanted here. So if you remember on the slide before, I said if you put different boundary conditions here, this will describe the possible kind of low-lying excitations I can get at the edge. But if the boundary conditions in the odd parity sector are 0, right? If this evaluates to 0, if this is constrained to the even parity sector, it doesn't make sense to put boundary conditions in the odd parity sector. It's not normalizable. It's identically 0. So this doesn't describe low-lying excitations. It just doesn't describe any state. So it tells me that also these guys, so the low-lying states at the edge are also constrained to the even parity. So again, there's this anomalous term, right? I have this completely normal dynamics at the edge, but it has a constraint to a parity sector, which again comes from the kind of topological order I built into my system. So we see that indeed all these things can be explained from the topological order in the bulk, which again is explained by a local constraint on the entanglement degrees of freedom. And these allow us to see how these anomalous terms, these topological terms, come along and why they should be the same both in the entanglement and in the dynamics and the physics at the edge. So, well, this tells us that PEPS, well, they provide a natural way, and that's maybe the main message, is really that they provide a natural one-dimensional space, right? Usually it's kind of very indirect via spectra and so on to see that entanglement properties are described by a one-dimensional Hilbert space. PEPS really give us an explicit one-dimensional Hilbert space describing the physics of these systems. And they give us really a way then to explicitly, via this Hilbert space, connect the edge physics, the entanglement properties, and the topological order in the bulk. 1 second. So I'm almost at the end. Exactly. So I just wanted to put up some summary. So I started by, just to summarize the main messages of the talk. So, well, I started by explaining the entanglement structure of many body systems, and the important thing was the area law. The entanglement scales like the boundary of the system, not like the bulk. This motivated the construction of matrix product states in 1 dimension and of PEPS in 2 dimensions, where we build the state up locally by taking some local tensor and building up the entanglement from local building blocks. This provides an efficient approximation of those states and also an efficient simulation method, which is very powerful to simulate 1-dimensional and also 2-dimensional systems. Then an important property is that they allow us to locally study the structure of many body states by locally encoding physical symmetries and seeing them in the Hamiltonian and in the global physics. Topological order in these systems can be explained from a local symmetry again, which allows us to fully understand the structure of the topological states. And PEPS give us a way to find some explicit 1-dimensional space for the entanglement properties, which allow us to make this relation of entanglement and edge physics much more transparent. And well, thanks for your attention.
Thank you very much. We have time for a couple of questions. Let's start here.
Hi, thank you very much for the talk. I'm curious about this section on edge physics. If I understand correctly, you're saying that the edge physics in a PEPS look a lot like the edge physics that we might expect from fractional quantum Hall states? Or at least in the entanglement spectra, is that?
Well, what I'm saying is that it allows us to understand the way in which the topological order in the bulk kind of is related or gives rise to some anomalous term in the entanglement spectrum and also in the edge physics and how they're related.
Does that mean we should expect that there is
But we're looking at different type of topological order here than the fractional quantum Hall, I guess.
Yes, that was my next question, was whether or not, is there a reason to expect that there is a PEPS-like description of the bulk of a fractional quantum Hall state?
Well, we're working towards it. We have this, I mean, these are chiral systems, right? So they're kind of different. I was talking mostly of non-chiral topological order. We have some examples for PEPS for chiral topological systems. The examples we have up to now are critical correlations. There are some results that with non-interacting models, it should be always critical. For general interacting theories, we don't really know. There's some argument in the community about that.
Thank you very much.
All right, take a question from the back of the room.
Can you clarify,
Sure.
when you talk about the low energy, hi Norbert, the low energy states of the edge, can you clarify that a little bit? Because it seems that if you put just one excitation in the bulk, then the energy is only increased by a constant. So, and my other question about it is why the low energy is relevant to constructing the entire Hamiltonian for it, because it seems like when we talk about the entanglement spectrum, you know, there's a statement really about the entire spectrum, not just the low energy state. So,
okay.
why can you talk about a structure just from looking at the low energy side of it?
Okay. I think we have different conceptions of what low energy means, right?
What's yours?
You think of PCP theorems probably. Energy is proportional to the bulk, the extensive energy. No, low energy means low compared to the gap of the bulk system. So if you wouldn't have a boundary, this sets a scale from the gap of the system, and low energy means significantly below the gap. which kind of means, I mean, that's exactly what you want for the excitation to be localized around the edge. Because once the energy goes on the level where you can create an excitation in the bulk, you cannot faithfully say that it's localized at the edge.
Right.
So when people in condensed matter say low energy excitations, they mean below the bulk gap usually. The second part, indeed, the entanglement spectrum is not completely identical to the edge physics or so. I think I was a bit sloppy. Like if you look at this entanglement spectrum, where is it? Plot from Lee and Haldane. What they actually see is that the low energy part reproduces a spectrum you see at the actual edge, and which is actually, in that case, also built into the bulk wave function. And this you basically do by counting and seeing that that kind of counting and also finite size splitting corresponds to what you expect from a certain conformal field theory. But it's really about the low energy part of the entanglement spectrum. Again, the argument is that it should correspond to degrees of freedom close by to the edge.
We have another question here from the edge of the audience. Yeah. So yesterday, Steve mentioned a result, I think it was actually your result, that says that there's a tomography scheme for matrix product states by which you do tomography on the reduced local states and then solve the quantum marginals problem, like stitching together local information to do tomography. And so I guess my question is two parts. The first is, do you know or do you expect that this will generalize to two-dimensional systems? And that's part one. And then part two is, for states that exhibit topological order, do you expect that to kind of like introduce a nuance or throw a wrench in the works for a scheme that works this way?
Second, what was the second half of the question?
The second half is for states that have topological order. Because you reconstruct the state by only local information, do you expect that this scheme somehow has a nuance now or breaks down for states that have topological
part
order?
one, I think it will work. I mean, I didn't do this tomography work, right? So
Sorry about that.
I don't see why it shouldn't work in 2 dimensions, except that numerically, say, if you want to do actual tomography, it's much harder to get these things working in 2D. Regarding the topological part, indeed, you will not be able to resolve the exact topological state, presumably, right? Because the point about topological states is exactly that all ground states, say, look completely identical locally. That's why it's a good quantum memory, right? Because you encode the information in different ground states, and they look completely identical, so local noise will not be able to mix them. But of course, it also means that with tomography, you will never be able to reconstruct which of the states you had if you do it based on your local information. You will get one of those ground states, but not the one you started with. For that, you would have to do some kind of global measurement.
Right, thank you.
More questions?
In the case of Toric Code, you showed that the topological order can be understood as a consequence of a Z2 local gauge symmetry. Is this the only way to have a topological order in the PEPS formalism? Local gauge symmetries?
We don't have a proof for that. It's like in many cases, we know sufficient conditions, but we don't know if they're necessary. Presumably, yes, but I'm not aware of a proof, to be honest. I'm probably sure I mean, if you phrase it precisely enough, I will probably be able to cook up a counterexample, which is not against the spirit of your question, but against the concrete formulation. That's kind of why it's difficult to make a full statement, because you can always do funny things. You get loops and things could cancel. But I think in the spirit, probably that's the only way, but we don't have a proof.
Thank you.
Okay, maybe final question over there.
In general, if we have a low bond dimension PEPS representation of the system, can we build it on a universal quantum computer?
Well, there have been some papers about that, right? They use some extra conditions, some conditioning numbers and gaps. And other than that, the answer is yes. So in principle, yes, but you might need some additional conditions.
Okay.
Can I ask a small general question very quickly?
Sure.
Yeah. So it is a very general question I have that do you think the matrix product states can be useful in any way to construct the ground state of field theory?
Well, I mean, there are continuous versions of matrix product states, which can indeed be applied to quantum field theories, for instance. You can, of course, also discretize things. Okay. In fact, continuous matrix product states in some way also tell you what the right way of discretizing these theories is to put them on a lattice. So in principle, yes.
Okay,
you have to be careful with your cutoffs, but like you have to always be careful with your cutoffs in theories.
Yeah, we
right?
can talk about it. Thanks.
All right, so let's stop here. Let's give Norbert a big hand again.